Let's move on to energy levels. This is a very important phenomena, and it's very important to understand this. So, what are the energy levels? And by the way, when we are, talking about the energy levels, you would know by now that we are referring to the energy levels in the outermost shell. Okay, to the electrons in the outermost shell, like this over here, and similarly these outermost shell. Can anybody remember the phenomena? What is the energy levels on the, uh, what would be the energy level for these valence electrons in the outermost shell? The farther an electron is from the nucleus, the higher is the energy state, okay? Because they are loosely bonded, so they are mobile. They would just go crazy and try to latch on to, other neighboring atoms, considering there is some uh, a decent amount of force that is attracting them towards the center of the atom. And any electron that has left its parent atom, so once it is ejected, has a higher energy state. Okay, like I was saying, they go crazy when they leave the parent atom than any electron in the atomic structure. Okay, because the other electrons are still bonded and they're close to the nucleus of the atom, so the force of attraction is just keeping them tightly bonded, whereas the electrons which are farther away, they are loosely bonded. Any external force applied, they eject and they move freely in the space, and they have a very high energy state, like I mentioned over here. Now in this graphics over here, you'll basically three the kinds of materials. One is the insulator over here, and this is the valence band over here. Okay, in the valence band you have the electrons, so these are just electrons. Okay, these are electrons. Okay, when this electrons moves to a conduction band over here, okay, that is when they start taking part in the conduction. That is the free space which is available to them to just flow. Okay, and if you look at it, the gap between the valence band and the conduction band, it's pretty big, right? That's pretty big, and it's usually greater than 5 electron volt. And that's why insulators are not good conductors of electricity, because they need a lot of energy for these electrons over here to migrate from here to here. Okay, and therefore they are not good conductors of electricity. Whereas if you look at this right here, conductor, this is the valence band, okay, where the electrons are available, and this is the conduction band. So this distance between valence band and conduction band is very tiny. So that means a very small amount of force applied will cause an electron to move to the conduction band, and where they are available to, flow freely and take part in the conduction. Okay. Now, similarly, here in the middle, you see the semiconductor. Okay? Semiconductors, their distance between the conduction band and the valence band is moderate. Okay, not too close, not too far, but somewhere in the uh, moderate region. So again, valence band are the electrons which are in the outermost shell of an electron of an element, and then some energy or is applied, and when that is applied, they move from valence band to the conduction band over here. Okay, so all you see these minus signs or encircle minus sign, these are the electrons. Okay, here are some of the band gap energy. So this, you see this energy, it is also referred to as energy, we use EG, also referred to as band gap energy. Okay, band gap energy. And as the name suggests, band gap, that's the gap between the gap or distance between the valence band and the conduction band. So here are some elements over here. Germanium has a valence band of energy band gap of 0.67 electron volt, correct? Silicon has an electron band gap of 1.1 electron volt, and then gallium arsenide is 1.43 electron volt. Okay, so if I asked you Say your sun, you have a sun here, okay? Okay, sun emits band gap energy, and those energy levels are in the range from 0.8 electron volt to 2.1 electron volt. Okay, all right. So before I throw this question to you, I also want to explain you one more thing here, which is when I say here that germanium has a band gap of 0.67 electron volt. So any energy which is equal to this number, 0.67 electron volt or higher, will eject an electron from the valence band and move it to the conduction band. Any energy which is greater or equal to 0.67, okay? Now, your sun is emitting these levels in the range from zero point 0.8 electron volts to 2.1 electron volt. Which one would you choose as a solar panel material among these three? Germanium, Ge, silicon, Se, or gallium arsenide? Can I choose silicon here as a solar cell material? Solar cell material, silicon has a band gap of 1.1 electron volt, okay? So any energy that is above 1.1 electron volt is going to, you know, move the electron in the valence band to the conduction band over here. Or you can either use germanium also, but the germanium has a band gap of energy of 0.67 electron volt, which is not a part of this range, right? So what do you think could be a good solar cell material, germanium, silicon, or gallium arsenide? In case of gallium arsenide, the band gap energy is 1.43, right? So it will only cover or produce electricity when the band gap energy is 1.43 electron volt or above. That means a lot of energy, which is in this range right here, in this range 0.8 to 2 electron volt, will get wasted, right? For example, if the band gap energy coming from the sun is 1.1 electron volt, the gallium arsenide is not going to conduct electricity because it needs at least 1.43, not 1.1 electron volt, correct? Are you guys following me here? So what do you think among germanium, silicon, and gallium arsenide, which semiconductor material will make a good solar cell material?
Would it be germanium?
Yeah, germanium could be an option. And I'll tell you why germanium is not used as a solar cell material. The germanium is not considered as a good solar cell material is because of the low stability. It's very fragile versus silicon. Okay, silicon is a lot more stable and it's available in the abundance, you know, on the crust of the earth. Even though it has 1.1 electron volt band gap energy, but it actually converts most of the electrons or band gap energy that is emitted by the sun. Okay, it only skips which 0.8 to 1.09. It does not, you know, will not react to this range in the solar spectrum, but other than that, it is going to, you know, give a response to all the energy levels that emits out of the sun. So that is the reason silicon is one of the most widely used semiconductor material. There's also silicon has a good thermal stability. Means, you know, silicon can work in extreme high temperatures, whereas germanium cannot. So when you are making a product, you have to think of it. Okay, I want this material to last 25 years because if you, I'm sure you guys are doing research on solar panels now. The project is related to solar panels. Solar panels has an average life of 25 years, and then every year their efficiency decreases by 1%. Okay, so if they were first year they were efficient 25%, their efficiency will go down by 1% next year. Okay, so you have to consider all those things. And then silicon, that's the reason it's one of the most widely used because of the band gap energy it has, 1.1 electron volt, and also it's more thermally stable.